Okay, our next speaker is Madhu Khanna. She's Associate Director of the Institute for Sustainability, Energy and Environment, as well as being a Professor of Agricultural and Consumer Economics here at the University of Illinois. She's previously been a university scholar and a Leopold Leadership Fellow, and she's going to talk to us about whether farmer behaviour can offset the impact of climate change on crop yield. Madhu.
So I think Max did a great job of setting the stage for some of what I want to talk about, and that is to the importance of incorporating farmer responses to climate change and what evidence we have about the extent to which that might be able to mitigate the negative impacts of climate change. So of course, as you've already heard, there is this growing demand on agriculture. The demand for food is expected to double by 2050, particularly if you're looking at protein and general crop calories. The current evidence suggests that if we were to just take the yields, under business as usual conditions, they are unlikely to double global production if we want to keep the amount of land that is under agriculture constant. So we would have to, at the current rates at which yield is growing, we'd have to bring in more land, and of course that brings in environmental impacts that we would want to avoid. In my talk, I particularly want to focus on the impacts of climate change on the U.S. and the evidence we have of that here. And the U.S. is, as has been said this morning by Steve, a major supplier of corn and soybeans, and so it's important to look at what might be the impact of climate change over here. It's also been mentioned that a large part of our crop production is irrigated, and so looking at irrigated versus dry land production is also key to understanding these impacts. And then, we're concerned about increasing yields, but at the same time doing that without increasing our chemical and other inputs, at the same time sort of trying to reduce soil erosion, nitrate pollution, and so on. And of course, increasing these yields in the threat, with the threat of climate change is going to be even harder. If we look at, this just sort of looking at the current projection for yield trends across the globe, and the red areas are basically showing areas where yield is declining, and the green areas where yields are increasing and expected to double by 2050. So you could sort of see that there are some areas where yields may increase. There's a lot of heterogeneity in terms of where yields may increase, and there are others where yields are likely to decrease. So thinking about the ways in which climate change sort of can impact agriculture, there is of course the direct effect of climate, and it could have a beneficial impact. We've heard a little bit about the CO2 fertilization benefits. And then it could have these adverse negative effects because of rising temperatures, changing patterns of precipitation, and there's concern about these potential nonlinearities and thresholds. There's also the concern that there could be modification of disease incidence, of pests and weed, and that could affect yields. And then there is changes in management practices that are going to be induced because of climate change, in particular looking at what happens to planting dates, because you have the frost continues much longer in the spring, or we have a very wet spring. That can affect planting dates and yields and acreage. And then in addition to these direct effects are these indirect effects that could happen, because as was also said this morning, you can, when climate changes, yields change, prices can be expected to change, and that can affect the way that farmers respond and the efforts that they put in terms of their management practices, the crop varieties they're using, and so on. So there's these indirect effects that we would want to consider. Now, of course, in looking at the total effect of we're interested in the impact on total production. So we need to look at not only yield per acre, but what's likely to happen to acres under a particular crop, and that would depend on water availability. It'll depend on planting dates, which can influence which crops can be planted when. And then there'll be indirect effects because crop profitability is changing. So farmers may move from certain crops that become less profitable in some areas to other crops that are now becoming more profitable. And so that's going to affect acreage and total production. And of course, these effects are going to be varying across location. They'll vary over time, and they'll depend quite a bit on the speed of global warming. So just looking at some of this literature on what is going to be the impact of enhanced CO2 on yields, and so some of the work, of course, Steve and Andrew have been, leading some of this. And what this research basically shows is that, in contrast to what was thought about, earlier about, that CO2 fertilization can actually negate some of the negative yield impacts of temperature. Most of that research being done, in greenhouse settings, which are not that realistic. The recent work, and some of which that Steve talked about this morning, suggests that there would be an impact, but less than what was expected before. And so this graph shows that, in general, if you look across crops, the impact of this fertilization would be in the range of 10 to 20%. Now that's on experimental fields, and the extent to which that will actually be observed in actual fields will depend upon the availability of other nutrients, what happens to insects, pests, and diseases. On the negative side, looking at the impact of some of this, of temperature precipitation on yields, what we sort of see from some of the work that's been recently done for the U.S., looking at corn, soybeans, and cotton, suggests that temperature will have a nonlinear impact on crop yields. And so there are threshold effects, and if temperature goes above a certain range of 29 to 32 degrees for different crops, then yields can actually begin to decline very sharply, following that. The impact of precipitation is more mixed across these different studies. And so precipitation has sort of this inverse U-shaped effect, where increasing precipitation to some degree is beneficial, and then too much precipitation can hurt the crops. But the effect of precipitation is smaller, at least if we look at evidence, and these are studies that are using, data for 30, 40 years across, a lot of this is using county level data for, over a long time span, and trying to determine what the impacts of these variables is on observed yields. Carrying that sort of study forward, if they project the impacts under various climate scenarios for the U.S., if you look at, again, corn, soybeans, and cotton, it suggests, well, firstly, the study that Max mentioned would suggest that, by Lobel et al., would suggest that we're already observing some impact of climate on yields. In the U.S., it's about 2%, the reduction between 1960 and 2008. But moving forward, the study suggests that the impact could be very large, and in about 30 to 46% by 2100, if we have a slow warming scenario, and much larger, 60 to 80% if you have a much larger, if you have more rapid global change. So those are pretty dramatic and drastic reductions that are likely to happen, as suggested by these crop models. Okay. There's also evidence that actually corn yields are becoming much more sensitive to drought, and so looking particularly at the Midwest, and again work by Lobel, which suggests that a big reason why modern genetics has actually increased average yields has been because of increased planting density, reduced pest damage, and that's also increased the exposure of crops to drought conditions because of the denser planting. And so the graph here shows that as temperature increases and this vapor pressure deficit increases, you're likely to observe declining yields per acre. And it's also not only going to lead to a reduction in the average corn yield, but also the rate of growth of corn yield. The graph on the right shows that the yield also depends on the date that you plant the corn, and so as you delay planting, yields can go down because of that as well. So if we look at some work looking at what's been happening to planting dates, we can see that planting dates have been increasing over time. And so this graph is basically showing the day of the year by which 10% of the planting had been completed. And you can sort of see this upward trend, and that this early planting has actually contributed to 19 to 50% of the yield increase in the Midwest. And so what happens to these planting dates with climate change is also something that we need to look at. And this is just sort of looking at some of the information from last year. Because of precipitation, there is a delay in planting. There's been often delays in planting of corn, and so that's likely to have an impact on corn yields, because if it gets too late, then farmers switch. Instead of planting corn, they start planting soybeans. And so, in fact, that's one of the things that happened last year, is that there was an increase in soybean acreage because it was too late to plant the corn, and also because we have crop insurance policies that actually reduce the crop insurance coverage if you plant in late May. Farmers just switch to soybeans. So planting can have a direct impact on yields, but it can also lead to a shift in acreage from one crop to another, and therefore reduce the amount of total corn production, in this case, that might occur. Okay. So that's sort of the direct ways in which climate can impact yields. But then we also want to look at these indirect effects of climate change. And one of the issues with looking at these crop-specific models, which only focus on the effects of climate, is that they're inherently sort of assuming this dumb farmer who's just a passive producer that is kind of responding to climate. And it's not taking into account the possibility that farmers might actually proactively switch their management practices, change from one crop to another, and adapt to climate change as a way to respond to it. And therefore, so the other approach that economists have taken to try to understand the impact of climate is this Ricardian approach, which basically looks at the impact of climate on agricultural land values or agricultural profits as a way to sort of look at, to tease out the impact of climate. And one of the things, of course, this literature assumes that farmers have perfect foresight and they can respond perfectly, so they're clairvoyant. But that they do incorporate adaptation, and they're looking at the aggregate impact of climate change, not crop specific, but what is the total impact on land values. And then more recent work in this area is now beginning to also include the importance of spatial spillover. So it's not enough to just look at the effect of climate at one location, but climate in a different region can affect yields, because it affects water flows, and water availability and so on. So you need to look at the effects of climate in neighboring regions as having an impact on production in a given location. And then also that these effects are going to vary over time, and so it's important to look at that aspect of it. And so this sort of graph, it's been around for a while. It's one of those that kind of brings out this fact that actually adaptation can lower the adverse impact of climate on agricultural profitability if we move away from this crop-specific focus to a more aggregate focus across all crops. And so this graph shows that as temperature increases, you may have a slight increase, for example, in wheat yields, but then wheat yields might start to decline. And at some point, farmers may switch from wheat to corn. And so if we ignore that, we would say, well, as temperature goes up, they move from point C to point F, and that would mean a very dramatic reduction in agricultural profits. But the possibilities of adaptation mean they actually move from point C to point D, and they can mitigate the impact or even increase their profitability because of this adaptation. And so this potential for changing crops, changing practices can mitigate this. And so a number of studies have been done since then in using this approach across the globe. I'm just focusing on the ones for the U.S., which have looked at what is going to be the net impact, the findings are fairly mixed. They vary quite a bit in terms of the magnitudes, but a number of studies basically suggest that global warming can actually benefit U.S. agriculture because of this adaptation. The range varies considerably, and the scenarios that have been analyzed also vary. So the comparability is not that easy, but they are consistent and sort of showing that there is a substantial positive impact. but that the impact is likely to vary across regions. And so a large benefit for farms in the cooler regions of the U.S., which could benefit from an increase in temperature, and losses for farms in the southern and the western part of the U.S., where there's going to be water shortages and so on. And also in part we want that it's important to look at not only the negative impact on these grains, which is negative, but also on these warm weather crops, and that might actually benefit from climate change. Now, this work is, there's been further nuancing of this work, which suggests that, so before that, here there's some work trying to reconcile. We've got these crop models that suggest the big negative impact. We've got these Ricardian model that suggests this positive impact that varies across different regions. And so some effort at trying to reconcile those and come up with a net impact, in a book that was, by Klein, which looks at without carbon fertilization, with carbon fertilization, and so the net impact sort of is shown in that right column, which is still supposedly positive if we look at the percentage change in agricultural production potential for the U.S. by 2080. Now, more recent work has sort of tried to focus a little more on the heterogeneity in these impacts, and the earlier work sort of lumped together all of the dry land production, the irrigated production, assuming those impacts would be very similar. And so if we separate those out, we begin to see that actually there may be differences across different areas of production, where and that it's actually not correct to treat rain-fed and irrigated land as similar, because the cost of water availability, impact on water is going to be very different in these two regions. And what these studies suggest is that there could be a loss for the dryland counties, but a small positive impact for irrigated counties, and in fact the dryland counties could suffer losses of anything from different studies vary, but sort of $3 to $7 billion, looking into sort of mid-century, late century. But again, there's an impact where the northern counties would be gaining and the southern counties would be losing. So it's clear from this that there's a lot of heterogeneity, and we need to focus on local impacts and to rather than just looking at the average, which might hide some of the differences which that might occur. Now, one of the, of course, limitations of this approach is it's assuming clairvoyant farmers that they can perfectly adapt, which may not be the case. More importantly, this whole methodology really assumes that long-run prices are constant. They're going to be, irrespective of climate change, these prices are going to be constant, and that is why you can tease out the effects of climate on agricultural production, because if yields were to fall and prices rise, profits might go up. In fact, as we know that, when we had the largest drought, farmers made record profits because of that reason. So treating long-run, this method has to essentially treat prices as constant. It also treats, technology, market structure, availability of irrigation, all of that is unchanged, and these results are very sensitive to how we specify climate variables and what kind of samples and how we break up the sample between irrigated and dryland counties. And so this is basically showing that in fact a number of studies have looked at the impact of climate change on temperature through the impact on agricultural production, which suggests that output prices can go up quite a bit because of temperature changes, and so that causes some question about the use of assuming that in fact prices would not change in these previous studies. So an alternative sort of approach that we've been recently working on is trying to use a more reduced form model where we try to understand the impact of climate on yields, but incorporating both these direct and indirect effects on yield as well as on acreage to try to get a better sense of what would be the impact on crop production without necessarily assuming any particular behavior of the farmer. But the one thing that we do know is that a lot of these studies are using not field level data, but they're using county level data because that's what we have information on for a historical, 30, 40 years of data for the U.S., and we can match that with climate data. We can look at other things that have changed along with that. And so when you're looking at aggregate data at a county level, those yields are really an average over many farmers, and they depend upon which land is being used, how much acreage is being cultivated, what crop rotations are being used, what management practices, crop varieties, as well as farm policy, which affects how much flexibility farmers have to change from one crop planting one crop to another, as well as climate. And so, if you think about the acreage within a county is consisting of high quality land and some low quality land, prices are going to influence which land, how much of this low quality land is actually going to be used for production. And as more low quality land comes into production, average county yields will go down. And so prices begin to play an important role in influencing the average yield that we observe in a county, besides climate. And so based on that, we sort of hypothesized that the average crop yield in a county would be affected not only by climate conditions, but also price expectations of farmers. And we can think of various ways in the models looking at, are farmers making naive expectations? Are they, do they have rational expectations and they're in being able to perfectly forecast, or something in between? And it'll also depend upon policy. So farm policy plays a big role in planting decisions and crop choices and so on. And to the extent that these prices and climate are correlated, as we've heard this morning, ignoring ignoring that interaction would lead to this omitted variable bias and could affect our estimates of the impact of climate. So what we do is we try to include both these climate and price variables, and of course the impact of crop price on yield, could be positive or negative. We would sort of think that prices go up, people might, farmers would put in more effort and improve their management practices, improve their crop varieties, and so on. But on the other hand, higher crop prices can also bring in more marginal land and expand production, which could lower average crop yield. So the net impact is something that has to be just empirically investigated. Similarly, fertilizer price impacts can also impact crop yield because it affects land use, it affects the amount of fertilizer use, and so on, and then policy effects. And then in addition, it's also important to look at the effects of both climate and prices on crop acreage, so that you can put that together to look at the total impact on the production of a crop-specific production. So when we do this using this data we're using 30 years data, with for across the counties. We're focusing on the rain-fed region in the U.S., looking at corn and soybeans, and as you can see, that's sort of the data that we have. The model predicts reasonably well. And the observed trend in yields is marginally sort of increasing, and that's sort of consistent with some of the other studies because of improved varieties in recent years. But if we look at, we use this and we project out, if we look at what the impact of including these price variables is that it actually, there is a slight overestimation. If you don't include these price variables in your regression models of the impact of climate on county level yields, then you're actually overestimating to some extent, 4 to 8%, the impact of climate on crop yields. And then the other thing we find is that there is a significant positive effect of corn price on corn yields, and with a significant elasticity of 0.25, which suggests that in fact, when yields presumably fall, prices rise, farmers do respond or can be expected to respond in the future to some extent by using better varieties to increase yields. So there might be some offsetting and mitigating factors there. To what extent that happens is, of course, depends on the scenarios that occur in the future in terms of how much this is possible and how far they can go with it. And then if we use this model to sort of predict the changes in 2050 and then 2100 using predictions from the climate models for temperature, precipitation, what we find is that, across these different models, at least in the up to the 2050 range, those blue bars basically suggest that yields, and this is looking at corn, could decrease by 9 to about 11%. So there's quite a bit of consistency in the medium term in terms of the impact of climate change on yields. But if we are projecting to 2100, then there's a lot of variability across, depending on which climate scenario we consider. And you could see, from 16% to 35%, depending upon which model one believes in. With most of this impact really coming because of the effect on corn yields, with a small impact on corn acreage. So let me just sort of end by talking about some of the things that, a lot of these studies have focused on the effects on yield, but there are, many other ways that climate change can impact agriculture that has not really been quantified very well. And one of those is the impact that it's going to have on altering disease risk for various species. And again, this has been sort of demonstrated through field and experimental studies. But what the large-scale impact of that is going to be on crop yields, and how the climate change is going to affect the spread of infectious diseases, and what kind of outbreaks that might lead to. That still remains to be. That's an area of research that still remains to be investigated further. And then finally, while we know that, of course, agricultural growth is really key to reducing poverty and hunger, and there's been a lot of research on the effect of climate change on the availability and the production of food crops. But if we look at the other dimensions of food security, the access to food, food safety and contamination, the stability of the supply of food, again, there's a lot of room for further research there on how climate change is going to affect access to food, and what impact it will have on farm income and the value of assets for farmers, and therefore purchasing power. Again, looking at the effects on contamination, future price trends, and what variability in prices does for stability of food supplies is worth looking into. As Max mentioned, a lot of the impacts on food security are really driven by our local, and so it's important to look not only what regional climate change is going to do to food security, and then finally, it's we really don't know very much about how farmers would actually respond. What are the behavioral responses they're going to demonstrate? Similarly, consumers to real and perceived changes in local climate, which could influence the potential for adaptation and therefore for mitigating these negative impacts. So I'm going to stop with that. And
questions for Madhu? Let's turn the microphone on.
Hello. Thank you, Madhu, for this talk. I have a question. Mainly, I heard a lot of problems and not a lot of solutions, which makes sense. There's a lot that needs to be done in terms of quantifying what the difference is between climate change and price, and how that would affect farmer decisions. I'm wondering if you could speak to, if you could tell a farmer right now, what behavioral changes could be recommended. How far off are we, I guess, from giving a recommendation, or if you have something in mind right now, could you speak to that?
So hopefully you'll hear a lot more of that in the coming sessions. But this was sort of focused on what we know about these impacts, but not to suggest that it's all sort of downhill from here. There are, as Steve mentioned, there are ways to improve crop technologies, and there's that is potentially out there. There's also ways to improve management practices. Some of my previous work is sort of focused on looking at the role of precision technologies as a way to better manage the field and better apply input so that you can get more productivity per acre of land. GMOs offers another great potential to reduce pest damage, increase yields. So I think there are a number of technologies that already exist that are not being adopted to the fullest extent. And there's, in part that's because of, again, communication, a way of sort of issues of demonstrating profitability. As prices rise in the future, maybe there will be greater adoption. So I think that, there are ways around this, and finding ways to communicate, educating farmers more about the benefits of that would be a way to mitigate some of these negative impacts.
Thank you.
This follows on that question, and that is the help that's given to individual farmers. There's a lot of effort going on, the field print calculator, John Deere's software, how to look at not their field as a whole, but micro parts. Are there any of those that are promising? They're focused on increasing yields and decreasing inputs, but I don't have a sense that it is in light of climate change. Can you comment on any of the promising assistance that's being given?
Well, maybe just a little bit, but I think that is a challenge in that we are, our data, our access to data at subfield levels has increased dramatically with technology. We, with GPS and other ways to monitor the field, we know really we can pinpoint the heterogeneity in conditions, and in the yields we can measure the variability in yields within a field. I think that the big challenge is really being able to use all of that information to improve decision making, and where I think we are still lacking, and in part one of the reasons that we've had 50 years of research on how corn responds to nitrogen. But yet, when it really comes down to being able to pinpoint, well, if we know this is the amount of nitrogen at this point in the field, how much should we apply over there in order to get the maximum yield? We really cannot say that with great precision. Because a lot of the studies that have been done in the past have been based on whole field analysis. They're not based on point by point looking at how nitrogen yield in a particular location responds to nitrogen availability and application. And so some of our research needs to move away from this whole field aggregate way to looking at more of heterogeneity and site specific estimation. I know Scott Swinton, who's here, has done some of that work. So we've got this, there's this increasing emphasis on big data, which is to use millions of observations in order to determine patterns of production. Going from that to improving decision making is something that I think, that's the next frontier. So.
Thanks for the talk. I was sort of related to the previous question, and sort of one of the factors that I think that I was looking for, but I didn't quite get it. Maybe was how do we incorporate this sense of increasing volatility that is associated with sort of climate change? There's increased riskiness to farming. How would that kind of make investments maybe suboptimal? Like farmers' behavioral response to increased riskiness might result in kind of sort of suboptimal investments at the time of deciding acreage or inputs into crop. And how do we kind of incorporate that into the models that we have right now?
Right. So I didn't spend much time on that, but that is exactly one of the things where we try to do that, at least in the study that I just presented briefly. And I mean, again, it's sort of limited with the data that's available, so previous studies have really looked at just average temperatures or aggregate rainfall within the growing season. But as Max pointed out, and some of our work suggests, it's really important to look at month by month or at the growing season versus at the pre-planting, growing, and so on. You have to look at the stage of crop production, and also not just the average within, say, the month, but you also need to look at the variability. What are the maximum and the minimum? And so, our climate data does permit us to do that. And based at least on our research, we find that is important. The variability matters as much as the average, and the timing matters in addition to the total. So I think these climate models are improving in discerning the effects of all of these factors. Now, how farmers are going to respond to that, I think, remains to be seen. And providing, again, it comes down to communication and education in terms of how they might respond to it. And so.
Okay, well, I'd like to thank all of you for the engaging questions you've posed us, our three speakers this morning, and would like to ask you to join me in thanking all three speakers for getting us off to a great start.
Illinois.